How you doing? I'm Mr. Rose, and today we're going to continue our story about rolling motion. So things we know so far. We know there are two sets of motion, translational motion and rotational motion. And we know F equals ma is the law that rules both. We know if we apply a force to some rigid body, it doesn't matter if it's translational or rotational, it can cause an acceleration. And it causes an acceleration about the axis in the same direction as the force. We know that acceleration, by definition, changes its kinetic energy because its velocity is changing. We know if a change in kinetic energy happens, that happens because of a work. Work, by definition, our work energy theorem is a change in kinetic energy. If I have a change in kinetic energy, that means I'm applying a force over some distance. So if I integrate that from some initial position to some final position, I know my work is an F times dx. Lastly, I know that if I take the derivative of work with respect to time, I get what we know as power, and power is force times velocity. And all of that same physics holds true in our rotational world. We have a change in kinetic energy is that should be our I, our moment of inertia I, times omega squared minus omega naught squared. I know that that is a work. Work is a torque times our change in distance. As I said, that's just our d theta. And now if I if I take the time derivative of that, I get a power over torque times a rotational velocity. Take a minute to take that in. And now we're going to move forward to rolling motion. What rolling motion is, just to start, I have a picture here. This is a picture of the same wheel as it's rotating about, coming towards me. What I have defined here, S, is that same distance S of that arc length. We know that this distance S represents that distance S, and they're related by the radius R and that angle theta. This is a couple things. It defines if there's no slipping, and things that are staying constant, this point P, that point P is my point of contact. In other words, that's always staying below my center of mass as my wheel rotates this way. Also, we see that I have the velocity of the center of mass, the velocity of the center of mass, that velocity is staying constant. Now, if I take my time derivative of the distance with respect to time, I know that's how I calculate a velocity. I can say the same thing with my rotational velocity, d theta, with respect to time. That gives me my angular velocity, omega. So what we're going to do is we're going to differentiate this S equals R times theta. That's my linear or my arc length distance. We're going to differentiate that with respect to time to get our velocity about the center of mass. So I know for a fact my velocity about my center of mass is omega, my angular velocity, times R, that radius. The bigger R, the faster I go, and that's nothing new. Now what we're going to do is we're going to take the same wheel, and we're going to look at it from two different reference points. Instead of just rotating in a stationary motion, about a stationary axis rather, we're going to now start to put that wheel in motion. Our first reference point is going to be this tiny little person that we're going to put right at the center of our wheel. Our second reference point is if I'm standing way far away, where I'm just looking at the whole motion of the wheel. So from my first reference, or my first frame of reference, I don't see any motion. I'm traveling at this center. I know that I see the wheel turning with that constant angular velocity, omega. If I look up to the top of the wheel, I know that V is equal to the velocity of the center of mass, and it's moving forward. And I know if I look down, my velocity is the velocity about the center of mass, and that's pointing backwards, again at that point of contact P. Now let's talk about somebody that's far away, just looking at the motion of the wheel. Well, they're so far away that they don't actually see this wheel rotating. So they see this just as a straight translational motion. If they see translational motion, they see the velocity at the top, the velocity of the center, and the velocity of the bottom, all as the same, just the velocity about the center of mass. Now, if I take reference point 1 and add it to reference point 2, I get our final rolling motion. What's actually taking place? Well, I can simply do vector addition here. I see V center of mass, so that means the velocity at the top of this wheel must be 2 times the velocity of the center of mass. Again, I know the velocity of the center of mass is omega times R. I know that 0 plus the velocity of 1v is just V center of mass, and I know a negative velocity plus a positive velocity equal magnitude opposite direction as a velocity of 0. Now this tells us something that's kind of strange. What this tells us is at the bottom of a wheel, if the wheel is rotating, if you take a creepy look at my cell phone here, If I look at that picture, you can see the spokes at the bottom are stationary because the picture shows it comes out. The spokes at the top are blurry. That happens because the velocity at the top, as we see here, the velocity at the top of the wheel is twice that, the velocity of the center, and technically infinitely more than the velocity at the bottom. This is what we mean by not slipping. This shows us that rolling motion isn't just rolling, it's not just translational. What this shows us is that rolling motion is a combination of both rolling motion and translational motion. So now I want to focus on the kinetic energy. If I have the kinetic energy of this object, I'm going to focus on it from reference point number 2. I know it takes energy to roll that motion. So I know the kinetic energy of this rolling object is 1/2 I, where I is our moment of inertia. And I'm saying it's the moment of inertia at P, about that part that's causing rotation by definition. This is my axis of rotation times omega squared, that's the rotational velocity. Well, I know from my parallel axis theorem that I don't want to calculate the rotational inertia here, but I know that this is just a ring. If I know its rotational inertia about the center of mass, I know its rotational inertia about anything that is parallel to that axis. So I can apply my parallel axis theorem and know the rotational inertia at point P is I about the center of mass plus the mass of the ring, mr squared. Take that, plug it back into my kinetic energy equation. I'm going to say kinetic energy is 1/2 I about the center of mass, omega squared, plus 1/2 mr squared omega squared. That's just straight substitution. Now I should start to recognize something. R squared omega squared, well, that's just the square of velocity. Velocity is omega times r. Kinetic energy is v squared. This is my squared velocity term. So I can see kinetic energy is 1/2 I, the energy it takes to move, that's my moment of inertia, omega squared, plus 1/2 m v squared. Those two motions have to add to my total. Now what do we want to do? We want to add everything and make sure we can add everything together. So here I have a question. I have a ball rolling down a hill. The ball is uniform mass. Here I have a free body diagram of that ball. Ball rolling down the hill. It's at an angle of 30 degrees. 30 degrees just made it easier for us for our first calculation. Based on my free body diagram, we're going to come back to later, but I want a crooked axis to match, to be parallel with my plane. And the things that I want to find the speed of the ball at the bottom, and I want to find the magnitude and the direction of the frictional force, which I have as a script F. So first, you can't see me. First, I'm starting with conservation of energy. It seems the best place to start, and I just went through this long derivation of energy. I know that my total energy before has to equal my total energy after. I know my initial kinetic energy is 0, just like I know my final potential energy is 0 because it's on the ground. mgh, 1/2 I omega squared plus 1/2 mv squared. I know that, again, those two things are zeros. I didn't include them. Well, here I have my I about the center of mass. I know it's a solid sphere that was given in the problem. I is 2/5 mr squared. And now, as you can see, my faint black line, I can cancel out. Cancel the mass, cancel the mass, cancel the mass. Simplify it. I have g times h equals 2/10 r squared. And now what I did here is, again, I went back to this key. My velocity is omega times r. I sub straight into omega, v squared over r squared, plus 1/2 what I'm left with my v squared. Now here again, I can cancel out my r squared. And now I'm left with something that's simple, and I have my velocity in terms of things I can deal with. Do a little bit of math. You get a final velocity at the bottom of the hill that's equal to the square root of 10/7 g times h, which comes out to 4.10 meters per second. Now again, let's go back and look at my free body diagram. What we're doing to find the friction is essentially applying Newton's second law, which is why I have this free body diagram. I know that I have a force due to gravity going down. I know I have a normal force coming up. And my frictional force is at, again, that point P, that stationary spot where I have my frictional force going, pointing uphill. My purple vectors here are not actual forces. This is just breaking down the perpendicular and the parallel force. And here I can see that My parallel component is going to be equal to my frictional force. My perpendicular component is going to be equal to my normal force, if that's going to become useful. Move this over to the side so we can keep looking at it. And here I know I'm going to apply Newton's second law, F net equals ma, where my net force is my frictional force minus F parallel equals ma. Substitute in, I have mg sine theta coming straight from my free body diagram equals ma. Well, one thing that I can't do is I can't use mu times the normal force. I cannot assume that Fs is a maximum force. What I can assume, however, is that this force is causing that body to move. That, by definition, r, distance r away, force, that is my torque. I also know it's at a maximum torque because r and f are perpendicular to each other. So this frictional force is actually a torque. I know torque is equal to I times alpha. And again, I know by definition the torque is the radius r, how far away I am, from f, where that f happens to be my frictional force. I, again, make a simple substitution in for alpha like we've done before. Alpha is equal to negative a over r squared. Now, this is interesting because as this is rolling downhill, it's rolling in a positive motion. It's counterclockwise. But based on my definition of positive degree, positive up and positive going up the hill because I wanted my frictional force to be positive, it is now moving downhill with a negative translational acceleration. So be careful of that small caveat. Straight plugging in, negative I brought my negative out, is my multiplied by my acceleration, a over r squared, minus mg sine theta, equals ma, can't see, equals ma there. I collect all my terms, again, with a little bit of algebra. I know a is equal to my general expression, mg sine theta, over negative I over r squared minus mass, where again, I we defined before as 2/5 mr squared. That should come out to a negative 3.5 meters per second squared. Last part was what we were actually trying to find, the frictional force. My frictional force, just straight plug it into what we have. I times negative a over r squared, where again, I is equal to 2/5 mr squared. That should come out to a positive 8.4 newtons, which again agrees with my free body diagram. X is going uphill in the positive direction. Friction is going in the positive direction. I hope this was helpful. Please like, comment, and subscribe. I got it right that time. And that's it. I don't end these well. I'll work on that.